Kia ora, welcome to video 16 in the series Agile Algebra. This video we're going to look at a proof. The first part of the proof here is actually quite simple. Just take three fractions, add them together and show that the result is zero. However, the second part of the problem is actually quite sneaky. And yes, it says hence there, so the first part relates to the second part. Finding the connection between the two is actually the trickiest part. And I must say that in recording the solutions to this, if you look at the timestamp, I tried one approach, it didn't go anywhere. I paused, reflected, and then re-recorded the solution to make the video clean. Like always, try the problem first, have a good crack at it, and then we'll go through the solutions after the music. All the best. Okay, so the first part of this problem is not too bad. We need to show that the sum of the three fractions equals zero. We need to make them have the same denominator, and as we can see there, two of the denominators have got an a minus b, so if we stick an a minus b onto the middle one by timesing by a minus b top and bottom, the left fraction there has a denominator that misses a c minus a, so if we chuck a c minus a top and bottom on that, and the rightmost one, c minus a and a minus b, needs a b minus c. Okay, and then we can go left hand side is equal to c minus a plus a minus b plus b minus c all over a minus b, b minus c, c minus a, and then of course they're the numerators. All of the variables cancel each other, so we're left with zero. So that's a nice quick proof. How does that relate to the next part of it? So the connection between the first proof and the second quantity isn't so obvious. The idea is that we need to prove that the quantity is a perfect square, so the square root of it should work. You could just put the fractions together like we did in the first part. However, we've just proven that three fractions, those three fractions that add to zero, and if we go and consider this quantity, this is the insightful part. If I consider this dude and I square it, okay, now squaring that is going to bring in, it's a example of, let's just use a different color, it's an example of a plus b plus c all squared. That comes to a squared plus b squared plus c squared plus two lots of the paired products. Okay, it's something I've just learnt off by heart because I've used it numerous times, but you could go through the double brackets and make sure you multiply every pair of terms and you'll get it. So we've got that, that, and that, plus two lots of 1 over a minus b, b minus c, plus 1 over a minus b, c minus a, plus 1 over, oopsies, I've used that one already, b minus c, c minus a. Okay, so that term there we already know is equal to zero because that was the first proof. Bigger highlighter. Right, that dude there is equal to zero from part one. So what does that mean? Well, it means that if we take the square root of this dude, it's going to be the square root of this dude, which is just the square root of that because the rest is zero. And so working, I guess, with backwards logic, it means that the thing underneath that second square root is a perfect square, and the answer to it is just 1 over a minus b 1 over b minus c plus 1 over c minus a, and I'm going to say the absolute value of that technically, and the reason for that is when we have the absolute value of something like 5 squared, sorry, the square root of something like 5 squared, the answer is 5. The square root of minus 5 squared is also 5. We're talking about the positive square root when we don't put a minus in the front of it. So the positive root of minus 5 all squared is not negative 5, it's positive 5. So we can't just go and cancel off the square root and the squared. Technically, the square root of x squared is the absolute value of x.